Hello and welcome to the course Basics of Experimental Design for Cognitive Psychology. I am Dr. Ark Verma from the Department of Cognitive Science, IIT Kanpur. This is the second week and we have been talking about descriptive research design so far. But as I said earlier, I wanted to present to us a brief survey of the other two kinds of research designs as well in some detail before we go on to the experimental research design. So, in the last three lectures, two lectures probably, we saw about different kinds of descriptive research designs. We talked about case studies, we talked about observational research, we talked about survey interviews and questionnaires. Now, we move to a slightly different angle and we will start with studying a little bit about correlational research designs. Okay. Now, as we have seen before, correlational research designs are typically used to search for and describe the relationships between two variables. Say for example, you wanted to study and note two particular variables. Let us say, I don't know, you want to study the correlation between weight and height. So, what you do, you can very simply collect the weights of all the people in your class, you collect the heights of all the people in your class, and you perform a statistic. We will talk about that, and it gives you a correlation. The correlation comes out to be so and so. That correlation will tell you whether height and weight are actually related or not. There could be other factors as well, there could be any number of things that are contributing here. Okay. Another example, the one that has been given in this book by Stanger, is basically this thing of that a researcher might be interested in knowing the relationship between, let us say, family background and career choices. So, or say for example, between diet and disease, what kind of diets lead to what kind of diseases, or say for example, the physical attractiveness of a person, how beautiful or good looking a person is, and will that relate to the amount of help they will get if they are stranded in a public sort of place. Okay. So, you can ask any kinds of questions, you can collect data and you can compute the correlation between the two things. Let us say on a scale of 1 to 10, how does physical attractiveness vary? On a scale of 1 to 10, this is where 1 is least help, 10 is most help. When physical attractiveness is highest, do you also get the highest amount of help, or when the physical attractiveness is lowest, do you get no help at all, something like that. All right. Now, these variables, whichever you want to study, say for example, can be related in a variety of ways. There can be variety of kinds of relationships between variables, all right. And sometimes it could also be the case that there is not only the two variables you are concerned with, but there are other variables in play as well. Okay. So, let's try and see what kinds of relationships exist, and a more detailed discussion can be had then. This is an example cited in Stanger. This is the study of Scher and colleagues in 1994. They basically collected data from 20 participants, students, on two scales. One is the scale of optimism and the other is reported health behavior. Say for example, they wanted to so one of the measures is a Likert scale measure on optimism, how optimistic a person is, and on health behavior, what kind of healthy habits are people following. Okay. Now, in this, the optimism scale varies from 1 to 9. So, 1 you are least optimistic, 9 you are most optimistic. So, higher numbers indicate a more optimistic personality, and the health scale ranges from 1 to 25. So, where higher numbers indicate that the individual reports engaging in more healthy activities, eating good food, exercising every day, waking up and sleeping at correct time, and a bunch of other things, okay, maybe dietary restrictions and so on and so forth. Now, here one of the hypotheses, let us say, that the researchers are probably testing is that people who are more optimistic about their life might not be following extremely healthy habits, because they would think that whatever we eat, whatever we do, we are going to not have bad consequences in terms of health outcomes and so on. On the other hand, people who are less optimistic and slightly conscious about life decisions may probably be following more healthy behavior, because they constantly have this fear of, let us say, having a diabetes or a cancer or an hypertension and things like that, and therefore they might be following more healthy habits. Okay. Again, just a hypothesis, I do not even know whether these people actually went with these hypotheses, but just trying to give you a flavor of what might have been done. So, as the estimate of the relationship between the two variables cannot be made using just raw data, because there are too many scores. So, 20 participants On a scale of 1 to 9, somebody would have chosen 1, somebody should have chosen 3 or 7 or 9, and you have these different scores. And on a 1 to 25, between 1 to 25, several things must have been chosen. So let's say there are at least, if not more, there are 40 values to be analyzed. Okay, and these 40 values on the face of this is not organized in the best manner. So how do you go ahead? How do you start organizing this data? One of the ways is to try and have a visual representation about how the values are distributed in relation to each other. So in the next slide, I'll just show you a scatter plot of this data, where the x-axis indicates the predictor variable, and the y-axis has scores on the outcome variable. Each dot is the combined score of an individual on both of these scales. Look at this. Okay, so this is optimism, high optimism, reported health behaviors. You can see it seems to be a linear relationship, because this is covered by a line, and it seems to be interesting that few people who are optimistic, extremely optimistic, are also following good healthy habits. So let's try and analyze this. Again, remember, this is not a causal relationship, it is just a associative relation. So we will talk about this in a bit. Now, what is this plot? This scatter plot provided us with a visual depiction of the relationship between variables. For example, the scatter plot just shown, you could see that the points fall in a fairly regular pattern, wherein data from most of the individuals are located in the lower left corner, this side, or in the upper right corner. So there is this straight line, this oblique rising line that you saw. And this straight line is basically referred to as the regression line. Okay, this is also referred to as the best fit line, as it is the line that minimizes the squared distance of the points from the line. So it basically says how distant are each of these data points from this best fit line. Okay, let's discuss this now. So we will talk about this also. It tells us something extremely important. Okay, now, based on this kind of an example, you can work around that there are probably 1 or 2 or 3 or 4 different kinds of relationships that are possible between variables. For example, linear relationship. If the association between the variables on the scatter plot, the one that you just saw, seems like it's a straight line, so it can be called a linear relationship. What more? Sometimes, let's say, if the straight line indicates that individuals who have above average values on one variable, say optimism, also have above average values on the other variables, say healthy habits following, and both are sort of increasing in the same direction, that is what we call a positively linear relationship. All right. So you can look at this graph here. This basically represents a positively linear relationship. Okay. On the other hand, in some cases what you will find is that individuals who have above average values on one variable, but below average values on another variable, then the relationship could be defined as negatively linear. Okay. From the data that is collected, we see that it seems very similar to a positively linear relationship, but it could very easily, or in a different set of population, could be the opposite. Say, for example, more optimistic people feel that, oh, I will never get a disease, I will never be on the other side of the health, and therefore they will be following minimal healthy habits. Obviously, it's just a belief thing. So you can find with the same data across different populations, both are possible. What is true is basically reflect in the data once you collect the data. Now, relationships between two variables are not always in a linear form. Okay, sometimes the relationships cannot be linear or can be non-linear as well. For example, the relationship for a couple of variables cannot be presented or cannot be summed up by a single straight line. You can see the graphs here, D and E. Okay, here the relationship is curvilinear. In E also, you can see the relationship is curvilinear. What is happening is that values in one variable are changing in response to the changes in the values of the other variable, but these changes are not best described by a straight line. Okay, so there is some relationship. It's not that these variables are not related to each other. There is some relationship, but this relationship cannot be best understood by a straight line. So these are called curvilinear relationship. Okay. On the other hand, sometimes there could be no relation whatsoever in the two variables or the values of the two variables. So you can see here there is no relationship between the variables. That is why there is no discerning pattern here. and that is why this can be called an independent relationship. Changing one variable does not have any impact on the other variable. Okay. Now, you can see some interesting things here. This R that is here basically depicts the Pearson product moment correlation coefficient, and this tells us something about the nature of the relation. I will describe this in more detail, but because we have the figure here, let us talk about this. Now, this R is positive in a positive linear relationship, is negative in a negative linear relationship, is 8-2 here and 7-0 here. What does this 8-2 mean? 8-2 means strong correlation. If it were 2-2 or 1-6 or 0-5, then it is weak correlation. Okay, that is one. Similarly, the magnitude on the other side, minus 0.70 means strong negative correlation, moderate to strong negative correlation. But on the bottom, if you see, graphs C, D and E are basically showing R is equals to 0, which basically tells us when there is no relation, the value of R will be towards 0, tending towards 0, and in the other two, because the relationship cannot be summed up by a straight line, the R value is coming as 0. Other statistics might be able to tell us more about these kinds of relationships. All right, let's talk about some statistical assessment characteristics of correlations. So, as I was saying, this R was basically the Pearson correlation coefficient. This is the one that is normally used to summarize and communicate the strength. So, how what is the magnitude? 0.20 or 0.80, 0.20 is weak, 0.80 is strong, and the direction plus 20 or minus 20, plus 20 is positive, minus 20 is negative. So, strength and direction of the correlation is basically depicted by the value of the R, or this Pearson correlation coefficient. Okay. So, again something that I already told you. So, the Pearson correlation coefficient, frequently referred to as the correlation coefficient, is described by this letter R, and it is the number associated with the R indicates both the direction and the magnitude of the association. The direction is indicated by the sign of the correlation coefficient. So, plus or minus tells you whether it is a negative or a positive relation. The strength or the effect size of the linear correlation of this linear correlation is indexed by the magnitude of the number. So, 0.20, 0.60, 0.80, 0.90 that ways. Now, how do you interpret R? It is fairly simple. The calculation of the correlation coefficient will be discussed, again we will talk about that in more detail, but basically what you do is you also carry out some kind of significance testing, and whether the correlations are significant, let us say p less than 0.05 or 0.01. We will talk about this in more detail later, but the significant values basically tell us whether we can seriously take this relationship or not, whether we can seriously interpret that these variables are actually related to each other or not. And this will be extremely helpful in when you are trying to predict the change in values of variable B based on the change in values of the variable A. Okay. So, significant R indicates that there is a linear association between the variables, and thus there is a linear association between the variables this is the knowledge that you will be able to use about a person's score in order to predict the changes in the value of the other variable. So, for example, as optimism and health behavior, remember Scher's example, are significantly positively correlated, we can use optimism to predict health behavior. So, maybe what comes out of this is more optimistic people follow more healthy habits. Good. So, the extent to which, however, we can predict this is indexed by the effect size of the correlation, 0.40, 0.50, 0.60 and so on, and so which is the value of R. Now, each test statistic, as we know, also has an associated statistic that indicates the proportion of variance that this R can account for in the data. Okay. So, that is basically, for example, for R it is the R square, and it is referred to as the coefficient of determination, how much data this particular thing is explaining. Okay. Now, when the correlation coefficient is not statistically significant, this indicates that there is no positive or linear or negative linear relationship between the variables. So, this has to be also in the range of p value being significant. Now, if the R is non-significant, does that mean that the data is not useful and we should discard the data? No. The non-significant R does not necessarily mean that there is no systematic relationship between the variables. It might sometimes indicate that although one variable cannot be used to predict the other, the Pearson correlation coefficient is not able to provide a good estimate to the extent to which it is possible. Okay, so if the relationship is not significant, it does not say that there is no relation, but the strength is not there, the effect size is much smaller. This again, it represents a limitation of the correlation coefficient, because it is very common in curvilinear relationships. So other statistics are followed there. Now this can occur in other various ways also. For example, sometimes the data on one of the variables is in a very restricted range. Okay, so the size of the correlation may be reduced if there is a restriction of the range of variables being correlated. Okay. Let us take an example, the one that the book has, Stanger's book. This could occur, for example, when the sample under study does not cover the full range of the variables. So an example was the values on the SAT test as predictor of college performance. Now it turned out that the SAT scores and measures of college performance, such as grade point average, the relationship is almost is only 0.30, which basically depicts a weaker correlation. Why is this coming out as a weaker correlation? Because probably the size of the correlation is basically reduced, because students only with the highest with very high SAT scores anyways get admitted to college. So when you are looking at SAT scores distribution and you are looking at GPA distribution, the SAT score distribution will be in a very limited range. Because this is in a very limited range, its ability to predict this one will not be as much. Okay. So when there is a smaller than normal range or one or both of the measured variables, the value of the correlation coefficient will automatically be reduced, and this will not really represent an accurate picture of the true relationship between variables. So before you are planning to conduct a correlational study, we should have a very good idea about the distributions of the variable in the population and choose the one which basically carries a wide range of values. Typically, that is why you see correlational only studies typically have a larger sample size, because they do not handpick their participants, they will collect a large range of participants. So it used to happen a lot in bilingualism research, when the idea was that you divide people into low proficient and high proficient bilinguals. There could be this threshold, let us say threshold of 70 on a particular test, under 70 and below 70, and then you are carrying out your experiment and data. At some point somebody suggested that okay, we should treat this as values of one variable across a continuum. So now what you could do is you could actually dump all of this data together and basically look at proficiency having this range. So now the number of participants increases. Earlier there were, let us say 60-60 in each group, now you have 120 on the same continuum, and in that sense it basically allowed the people to understand the effect of language proficiency on other variables much better. Okay, look at this here. Okay, the correlation between high school GPA and college across students is about across all students is 0.80. However, since only the students with high school GPAs about 2.5 are admitted to college, the data are only available on both variables for the students who fall within this circled area. Within this circled area, you can see that the correlation is typically much lower. It comes down to 0.30. Okay, so this is in that sense interesting. Now, how do we report correlations? We are just talking about this. So when the research hypothesis involves testing or presenting the relationship between two quantitative variables, the best way to report is the R statistic. Okay. So if the null hypothesis is that the variables are independent, then R should be equals to 0. If the research hypothesis is that the variables are not independent, then it should have some value, either more than 0 or less than 0, some magnitude will be there. In some cases, the correlation between the variables can be reported in the text of the research report. For example, as predicted by the research hypothesis, the variables of optimism and reported health behavior were significantly positively correlated in the sample. You can see here we have indicated the sample size for R, we have indicated the value of R, and we have basically also indicated whether this is a significant value or not. All right. Now, sometimes there are many variables involved. Okay, when there are many variables involved, then how do you present the correlations? Then you typically present them in a correlation matrix. You can see here there are 4 variables, and basically they are all related to each other as well. So this is basically how they are reported. The one with the asterisk are the ones that are significant. Okay, all correlations are based into n is equals to 155. Here is also a correlation matrix that comes out as an output in the IBM SPSS software. I am sure everybody knows about it. Now, this is one way you can present a correlational matrix, but sometimes you are interested in knowing what are the different variables that are playing a part. So, we carry out multiple regression. As we know that the primary objective of correlational research is to investigate the relationship between variables, it is also possible to study the relationship among many variables, okay, or more variables. For example, if the researcher's objective were to predict the GPAs of a sample of college students, and the scientist decides to use three predictor variables: perceived social support, number of study hours per week, and the SAT score. So, now there are three variables that the person is interested in. Now, in such a research design where there is more than one where there are more than one predictor variable, then what you are conducting is called a multiple regression. It can be multiple predictors and a single outcome, and either ways. Okay. So, multiple regression is basically a statistical technique based on the Pearson correlation coefficient, and basically what it does is correlation coefficients are calculated between each of the predictor variables and the outcome variable, and among the predictor variables as well. Okay. So, there are several predictor variables and there is one outcome variable. All of these are trying to predict how does college performance fare in terms of perceived social support, in terms of number of study hours per week, and in terms of SAT score that they had initially obtained. Look at this, there are different predictors and there is one outcome variable, and you can see the correlational sort of values that are here. Okay. So, social support 0.14, study hours 0.19, and SAT score is 0.21. So, this is broadly what we are getting. This one is not significant and these two are significant. Now, typically because there are so many of these correlations to compute, this is typically done using softwares and computers, but two important pieces of information are very important. First, the ability of all the predictor variables to predict together the outcome variable. So, this is indicated by what is called the multiple regression coefficient, the capital R. And just as the small r had r square, there is also a capital R, which is basically the amount of variation, the proportion of variation that is explained in this data. Okay. So, there is the r square. R square is the proportion of variance measure, and both can be directly compared to r and r square, because it is broadly these are just correlations. Okay. Second is that the regression analysis may show that statistics indicate the relationship between each of the predictors as well. So, that is why in the correlation matrix you can also write down correlation values between variable A, B and C also. Okay. So, these are called regression coefficients or beta weights. Okay. Now, each regression coefficient can be tested for statistical significance. So, you can say these are significant, the others are not significant. So, that is why p values are indicated by means of an asterisk on the correlation matrix. You can see here. Okay. So, this one is not significant, this one is significant, this one is. So, you can basically see you can, when you are putting this in the paper or in a table, you will mark a star here and a star here, and this is the regression coefficients. Also understand the regression coefficients are not exactly same as the zero order correlations, because they represent the effects of each of the predictor measures in the regression analysis, holding constant for or controlling for others. So, remember, because you are performing a multiple regression, these b values here are not the same as the value of r that we have seen earlier. This value of b is arrived at controlling for this one and this one. So, this is the overall contribution of social support when you have controlled for study hours and SAT scores. This one here is the contribution of the study hours controlling for social support and SAT score. The outcome variable is GPA, and this one is the contribution of SAT score in GPA controlling for study hours and social support. So, I think that should be clear. That is why the beta weight is written there. So, that is why the B is there. Okay. The result is that regression coefficients can be used to indicate the relative contributions of each of the specific variables. For instance, the regression coefficient of, I should have written B is equals to 0.19 indicates the relationship between study hours and college GPA controlling for both social support and SAT. That is what I was telling you. Okay. In this case, you can see that the regression coefficient was statistically significant, and the relevant conclusion that you can make is that estimated study hours do have a power or propensity to predict the GPA in the college. Alright, so this is a little bit about the correlation style of research that I wanted to talk about. I will continue this in the next lecture. Thank you.